Welcome everyone. Today we're at Freres Lumber Company in Lyons, Oregon, and we're in the cogen plant. This is part of the electrical bank because when you do cogen, as hopefully you already know, you make both steam and electricity. So this is part of the electrical output or control. And our guide today is going to be Scott, who has many years of experience in working with bioenergy. And so he's going to lead us through and show us how the plant works. So Scott, how long have you been here at Freres?
So I've been first of all, welcome to Freres Lumber Cogen Plant 5. I've been here at Freres for approximately 2.5 years. I spent the majority of my career in the waste to energy space, about 33 years in steam power generation prior to this.
And what's your official title here?
So I am what they call a relief operator, trainer. So basically what that means is I help train the operations staff and personnel at the facility around the biomass and energy processes that we do here, and I relief operate if somebody's on vacation or sick or any of those things. I can step into the operator position and operate the facility.
So what we were talking about before was this is a much bigger operation than just burning Freres' sawdust. So can you tell us what kind of feeds waste wood that come into the plant?
So we receive biomass fuel, that's our fuel, from several industries throughout neighboring counties in Oregon. We receive about 53,000 tons of biomass waste a year. We process about 20% of that comes from the facility itself, from the grinder pile or from other processes in the facility. With that BTU value we receive from that fuel waste, we produce about 48,000 megawatt hours annually, or 5.9 megawatt hours per hour, which is about enough to power 5,000 homes 24/7.
So the waste comes in mostly in trucks or
in
trains,
trucks.
or it's all in trucks?
They enter the facility, cross the scale. Once they cross the scale, they come to the truck dump, which we'll walk over to and take a look at next, where they call the operator. The operator will ask them what their weight is. We have a dry silo and a wet silo. So biomass comes in different moisture content, obviously. So we put the wetter waste in the north silo and dry waste in the south silo, and then we mix them together to get a homogeneous blend before we feed them to the boiler.
Okay. In terms of kind of the physics of what's going on, do you add any, because you're making both steam and electricity, right?
Yes.
So if you need more steam, do you add water to the boiler, or if you need more, or does all the steam that you make come out of the wood?
So it's really based on the BTU value of the fuel. So we have a 2-cell double drum Zern 100K, 100,000 pounds per hour water wall boiler. Based on the BTU value and time of year, which affects the BTU value of the fuel, dictates what load we can run. Right, so typically we're about average over the course of a year about 5.9 megawatts per hour. That's average. We can produce up to 10, but an annual average is 5.9 an hour.
Okay, so do you supply 100% of Freres Lumber's needs for steam and electricity?
Not for electricity. So we sell electricity to the grid, to Pacific Corp, and it goes out into the electrical grid. For steam, yes, we provide 300-pound steam to plant 4 for the process, 65-pound steam to plant 1 and 2 for their processes. The rest of that steam goes to the turbo generator to make power.
Okay, all right. Very good. So Freres is self-sufficient in steam.
Correct.
But not electricity.
Correct.
Is that a choice because they already had the electricity, so when you put in the cogen plant, they didn't rewire everything? Or
so the cogen plant came later.
Yeah.
So Freres Lumber is a 100-year-old company, right? Family-owned 100-year-old company. It really started north of here up in the mountains as a logging camp, and then transpired into what you see today. But the cogen plant came later after the initial infrastructure was in place.
Yeah. So
the idea was to make process steam, right, for the plants and support them that way. And then the power we just sell to Pacific Power.
all the power goes to the grid.
Yes, sir.
All right, very good. So now we're going to walk through the process and actually have a look, and we'll all get to see what's going on here. All right, Scott. So the trucks dump here, and then what they dump moves up. You can see where it moves up into this whole complex of silos and storage facilities. So why don't you tell us about what's going on here?
Okay, so once the trucks come across the scale and they're weighed, they'll pull forward and back onto the truck dump. They'll call the operator via a radio up in the control room. The operator will typically ask what their weight is. That's how he judges how heavy or dry the fuel is, gives him an idea of the BTU value of the fuel. Once the truck dumps, the operator will select a silo. We have two silos, silo 1, which is our wet silo, silo 2, which is the dry silo. Inside silo 2 is a mixing auger that feeds into that main fuel conveyor, where we can mix the dry fuel with the wet fuel for the most homogeneous mix and the most consistent BTU value. Trucks back onto the truck dump, tip onto the chains. The fuel goes down conveyor 1, where it crosses underneath a ferrous magnet, where they'll pull out metal and all kinds of other things that we don't want in our process.
Right.
Up belt 2 to a disc screen. Sometimes the fuel they bring in, although it's gone through a grinder, will have bigger items that we really don't want that'll plug up the process. At the disc screen, those big items are removed. Then the fuel travels up and goes into silo 1 if it's wet, silo 2 if it's dry. Once we have a good inventory in the silos, the rest of the fuel during the week goes into the fuel shed right there. And the fuel shed is to sustain us on weekends, holidays, when we're not receiving fuel during work hours. So we have to get through those periods. So from a Friday, that fuel shed will be full, and on a Monday, it will be relatively empty because we'll have processed that storage.
So what would happen if you didn't mix the wet plus the dry before you fed it into the generator section?
So if we don't have a good homogeneous mix of the fuel, wet and dry, if we just slug feed wet, the boiler tends to operate like this: down and load, up and load, down and load, up and load, right? You'll get a slug of wet fuel and the load will go down, the megawatts will go down. You'll get some dry fuel backing it up, and then it'll come up. And we want to have a nice, smooth line, steam flow line across there. So it's very important that we have good dry fuel in 2 and to mix with the wet fuel in 1 and keep that homogeneous mix as close as we can.
Does Pacific Power get upset if your feed to them is going up and down, or is it because of your equipment?
Not necessarily. It's because of the equipment, and it's not profitable, right? If we can sustain 5.9 megawatts, which we averaged last year per hour, versus 2, 8, it's sustaining that megawatts, trying to keep it smooth so that we can get the most money we can out of the power we're generating.
Very good. All right, shall we go look at the shed?
Absolutely.
Okay, Scott, so I just want to make the point here that you have 2 sources of waste, and this is one. This is the pile. The pile here is the waste from the plant, from the mill, from Freres, right?
Absolutely.
And then it comes from the pile, it goes into this
grinder,
the blue machine here.
The grinder.
That grinds it all up, and then it comes into the truck. The truck drives over to where you dump the truck.
To the truck dump, yes.
So that it can go into the storage, either one of the 3 storage places.
You got it, hit it right on the head.
All right. you can see here where the trucks have been dumped, and the fuel then goes up and goes into this shed or into the silos. But Scott, why do you have a shed and silos?
So the silos are what we use day to day, right? Monday through Friday, most of the time for our fuel, right? So we fill those things up to 100 plus units, and that will sustain us through all day, all night. Weekends, holidays, when we don't have inbounds fuel, we have to have enough stored to keep the plant running through those periods. And that's where the fuel shed comes in. We'll have enough fuel in there to get us through a 3-day weekend easily. The operator will come out, dump into what we call a reclaim. And that's that hopper right there. And that reclaim has a conveyor that then goes up and fills the silos for us out of the fuel we take from the shed.
Okay, so the fuel can go directly into the silos, or it can go into this shed, which is what they use when they're not getting regular shipments of fuel. And also, I think you said that the waste from Freres, which is in that waste pile over there that we just looked at, that also goes into the shed here, right?
Yeah, once they grind it into biofuel, then trucks from the grinder pile will back up and dump just like a commercial truck from offsite.
Okay. And then because the fuel that's in the pile is wet, it's going into the shed, because in the shed you can they mix the wet fuel with the dry fuel using the
Front end loader
in there.
We try to put the dry fuel in the back and the wet fuel in the front, and we can push the dry fuel over the wet fuel and mix it. It's kind of it's a more rudimentary way to do it, but it works.
Okay, all right.
So once the silos are full, silo 1's full of wet fuel, silo 2's full of dry fuel, we're mixing the wet and the dry. It then goes into the main fuel conveyor, where it is transferred up to cell 1 metering bin and cell 2 metering bin. And that's what we're about to go look at now, and we might see a little fire while we're at it.
Okay, Scott, so the fuel comes in the chute up here, then what happens to it?
So it comes in, that's the main fuel conveyor from outside. It comes in and drops into a transfer conveyor. From the transfer conveyor, it drops into cell 1 and cell 2 metering bins, and then into cell 1 and cell 2 feed auger, which are right over here. From the transfer conveyor into cell 1 and cell 2 metering bins, and then into the cell 1 feed auger or cell 2 feed auger. We'll pull the lid and you can walk over here and I'll show you that fire I promised you. From here, we would go down to the basement on the other side. The fuel is falling into the cells. We have a combustion air fan that is blowing under fire air, over fire air, and top over fire air into the cells for combustion. And then that hot flue gas comes up to the upper furnace where it starts to heat up the water in the tubes. And to see the cells, we can go downstairs.
So we saw the fuel wood dumping into the furnace, we saw the fire, and now we're at the bottom of the furnace, and what's going on here?
So cell number 1, cell number 2, that fuel that we saw falls on top of these grate surfaces. These little rolls here, from here, this direction is cell 1, from that control box, that direction is cell 2. That fuel falls on top of those grate rolls, makes a mound. We use flue gas to heat the combustion air that comes in, and blow underneath through those rolls to stoke the fire.
So you have a fan that pushes air through this big, huge air duct here.
Yes, sir.
Right? And it comes in this metal, silver metal part into the furnace.
Into the furnace. We call that combustion air.
Yeah.
The grate rolls are on a timer. The operator sets up a timer as to how often they roll. That's how he controls his fuel bed depth. Okay? When the grate rolls roll, the inert ash goes through the grate rolls into the main ash transfer conveyor and out to the ash collection system that we can talk to later. The heat from the combustion process, flue gas is what we call it, travels up into the upper furnace where it heats the water in the water wall tubes, passes through the convection section, the superheater, where we heat the water turn it into steam. That steam is 850 degrees Fahrenheit at 820 pounds per square inch. From there, we send the majority of that to the turbine generator, but we also support the steam demands of plant 4, which is process steam, that's 300 pound steam, and the steam demands of plant 1 and 2, which is 65 pound steam. So we're supporting their processes with the extra steam generated through this process.
Let's go look at the next step. Okay, Scott, so we're still following what's left of the wood, because the wood's all burned up now, but we have both ash and flue gas that come out and go up into these air handling structures. You can tell us what they really are.
Yep.
So tell us what happens now.
Okay, once we combust the wood in cell 1 and cell 2, the grate rolls roll and the inert ash falls through the grate rolls into the main ash conveyor, and we'll get to that in just a second. The flue gas that travels up through the boiler that heats the water in the boiler tubes up to 820 psi at 850 degrees Fahrenheit, which we send to the turbine generator, plant 4 for process and plant 1 and 2 for process, continues out. That ductwork at the top of the building is where it exits. It comes down to what we call an economizer. So the idea is to take every bit of latent heat we can out of that flue gas. We want to get all of it.
Yeah.
So we preheat what we call feed water before we send it to the boiler with the latent heat of that flue gas. It then travels down into an air preheater where we use the latent heat of that flue gas to heat up the combustion air prior to going under the grate rolls for the combustion process. Then it travels out into what we call a cyclone separator. A cyclone separator is the first line of defense for particulate emission. What it does is it causes that flue gas to go through a rigorous path, and any heavy material will fall out into the ash system. From the cyclones to the ID fan, induced draft fan. That means it is pulling a negative pressure on the boiler, to the electrostatic precipitator, or the ESP, and then out the stack.
You blow air into the bottom of the boiler and you suck flue gas out of the top.
Absolutely correct. And then we have emission monitoring on the stack in the way of opacity. So we measure the amount of opacity, and we are limited in the amount that we can emit by a Title V or an air pollution control permit.
Because opacity means smoke.
Or particulate emissions, or visible emissions.
Yeah.
Stuff you can see.
Right.
The ash comes out into the main ash conveyor, goes up through a set of double dumps into a rotary trommel, which is right there.
What's a trommel?
So a trommel is basically a drum that spins with a screen mesh on it, okay? So larger size items won't go through the screen. they travel this way, like coarse ash, metal, and rock. Fine particulate ash goes down into an ash transfer conveyor and out to the ash cone right there. Once we get to the ash cone, we'll talk about the biochar process.
Okay.
The bigger ash that comes out goes one of two ways. The wood ash, which we call coarse ash, goes into that box right there. Now that coarse ash, we also reprocess that. That is unburnt combustible wood that we will reprocess. We will dump it in a certain area for it to cool down, and then we will reclaim that back to the silos and reprocess it.
Like that.
Exactly. Behind you is a water bath. The water bath does two things. It separates the rock and metal from the coarse ash. The coarse ash will float, and the chains will take it to the west and deposit it in this box. The rock and metal is heavy. It sinks and travels this way. Then it goes up a rock belt. In this rock, there is ferrous metal in the way of nails. There is a magnet at the head pulley of this belt that is separating the nails over into a metal bin. And then the rock ash goes into a rock box, which goes out with the waste ash.
Okay, Scott, we've been tracking the wood now. The wood's all gone, it's burnt, except for a little bit of the wood we saw in the 3 bins over there.
The coarse ash.
Coarse ash, it was wood that didn't get burned. That's gonna go back and get burned again. And then the rocks came out and the metal came out. And then there are small particles that didn't get separated in that process, and those particles, they went to the electrostatic precipitator. The big thing behind me, the really high one, it precipitates fly ash, right? So tell us about fly ash and what's going on here.
Okay, so there are 2 types of ash produced by the combustion system: bottom ash and fly ash. The bottom ash we just talked about with the rock, the metal, and the coarse ash. The fly ash tends to stay entrained in the flue gas and falls out in hoppers. That fly ash falls out into a hopper and then is sent to this ash cone above us. From that ash cone, we are screening the fines out of the ash that we're calling waste ash. The larger particles, the biochar with all the carbon content, we're collecting for beneficial reuse. By beneficial reuse, I mean agricultural reuse. They use it in chicken coops. They bag it and people can buy it at the store and put it in their flower gardens so that they can re-get that carbon content back into their soil. So this is currently a pilot program that we're just getting off the ground, but that is the intent down the road.
So here we are in the control room for the cogen plant at Freres Lumber. The operator for the plant is Brad, the fellow sitting here in the chair, making sure everything is going according to plan. And now we're gonna talk about not only the control room, but Scott's gonna talk us through what happens to the water, because the generator that makes the steam that makes the electricity needs water. So Scott, how's that work?
All right, so we pretty much walked through the entire process out in the facility. So here we are in the main control room. The operator has pretty much a visual on everything that's happening out in the facility, as you can see by all these monitors. He can start, stop, control all the equipment here. He can control the combustion process and pretty much everything that happens in the operation of this facility. So what we have here is a closed loop system. We've talked about steam, we've talked about steam to the turbine generator, we've talked about process steam. Now we're going to walk you through water to steam and back to water. We have two sources of water here at the facility. One is well water and the other is city water. We use city water for the boiler side process. That water comes into the facility, goes through a dechlorination system, then an RO, reverse osmosis, which
Why
is
do you take
really,
the chlorine out?
well, chlorine is very abrasive and corrosive when you're talking about boiler tube, especially at the temperatures and pressures that we operate. So we do that to prevent waterside corrosion. There's waterside corrosion, there's fireside corrosion, and we're talking about waterside corrosion with chlorine. We go through an RO, reverse osmosis, which is really just a very stringent filtering system, membrane filtering system, to purify that water, and then it goes into a 10,000 gallon storage tank. Once the boiler is full, we fill what's called a deaerator, a DA tank, which deaerates, stores, and preheats the feed water. So we want to make the boiler fire as economically as possible, so we use as little fuel as possible. That's why we talked about preheating the feed water in the economizer with flue gas with the latent heat. That's why we talked about preheating the combustion air with flue gas. That's latent heat. Everything to make things more efficient. Once we store enough, the boiler's full, store enough water, deaerate, preheat the water then goes to feed pumps, which pump the water into the boiler steam drum. The flue gas from cell 1 and 2, where the fires are that we looked at, comes up through the cells into the upper furnace. And it heats that water in those tubes up to 850 degrees Fahrenheit, 820 pounds per square inch. That boiler leaves the steam drum, and the majority, or that steam leaves the steam drum, and the majority of the steam goes to the turbine generator at 820 psi. We have several reducing stations upstairs for process steam. We call it a turbine bypass. So we reduce that steam pressure from 820 to 300, and we send that to plant 4 for the dryers, 1 and 2 for
Those are
process.
the dry kilns, right?
Exactly. We further reduce that steam to 65 pounds per square inch, and we send that to plant 1 and 2 for their tunnels.
Well,
Now-
what are the tunnels?
The tunnels is where they dry the wood. Talking about a closed loop system, when we produce that steam, we need that condensate back, right? We'd never be able to supply enough water to that boiler to keep it running if we didn't get that condensate back. So we get condensate back from plant 4. They use that steam, they take the work out of that steam, they take all the thermal energy out of that steam, and they send the condensate back. Goes to a dryer condensate tank and then back up to the DA. Plant 1 and 2 use 65 pound steam. They take the work and heat out of that steam, and they send the condensate back, and it goes right back into our process. The steam that we send to the turbine generator, after we take the work, the horsepower out of that steam, we recondense that into a condenser, which goes to a hot well. Once it's turned back into condensate, that goes back into the process. You asked about the cooling tower outside a while ago. So, the cooling tower outside is really like a big radiator on your car, okay? So look at the turbine generator as a big motor, right? Every motor has
It's actually
a
a motor
radiator.
running backwards.
Exactly. So once that steam travels through that motor, it goes into a condenser where it's recondensed back into condensate, and those fans on top of the tower are what's keeping that cooling tower water cool by evaporating the heat through stacks with airflow out of the top. Any questions on any of that? That's
And
pretty
that
much the
completes-
process.
so
that
Not
completes
only
the
is
system.
the wood going through a circle here, the water's going through a circle.
Absolutely.
And nothing is thrown away, although some is lost to evaporation and leaks and stuff like that. So you have makeup, but in general, it's a closed cycle.
It's a closed loop. Yep. So these screens that Brad sits in front of are all his combustion controls. This is how he controls fuel feed rates. That's how he brings the load up and down. His stoker controls over here are how he controls the grate rolls that I showed you down there, which feed the bottom ash system. And the emission controls here. So this is under our Title V permit currently, we are regulated on opacity. So that is the current opacity, 1.8 peat part per million coming out of the stack right now. So well below the threshold. Our permit limit's 20.
Environmentally clean.
Yep, clean, renewable energy. That's what we make here.
Tell us about the generator.
Okay, so that is a GE turbine generator set rated at 10 megawatts. It's 13.8 and 69 or 67 kVA out to the grid. Currently, the operator is doing about 6.6 megawatts. So the boiler is putting 82.8 kpph or 1,000 pounds an hour of steam to the turbine generator currently. The generator or the turbine is taking the work out of that steam, spinning at 3,600 RPM and turning that generator to produce 6.6 megawatts right now.
Is there any significance to 3,600 being divisible by 60, which is the cycles on the AC?
Absolutely. That's a two-pole generator. With a two-pole generator, 3,600 RPM is 60 cycles, and that's what America runs off of.
The condensed steam goes where?
Okay, so the condensed steam goes through an exhaust trunk after we take the work out of it, into a hot well where it becomes condensate again, and then we pump it back to the DA where it turns back into feed water, and we use it all over again.
So it goes right back into the boiler.
Absolutely.
Yeah. Okay.
Now, talking about the generator real quick, we talked about this earlier. So we produced 48,000 megawatt hours annually and 5.9 megawatt hours per hour, which is enough power to power 5,000 homes 24/7.
Even if you turn the thermostat up.
Even if you turn the thermostat up.
Okay.
Are you using all of the power, or is it being sent back to the grid?
So we don't use any of the power in-house. It's being sold to Pacific Power, so it's going to the grid.
The main reason for that is because, correct me if I'm wrong, is because they built the lumber mill before they built the cogen plant. So they didn't want to change all the electrical circuits in the mill for the cogen plant. So they just sell all the electricity to the grid.
Yeah, the infrastructure at the time that this was built wasn't in place to do that.
So that completes our tour of the Freres Cogen plant. It was a good tour. Scott did a great job, I thought, and I really want to express my appreciation to Freres Lumber Company for all of the times that they have helped out OSU, the College of Forestry, and the Department of Wood Science. They're a good friend, and I'm glad we got to come visit with them today.